Okay, so our next video is finding points on a curve with a given angle of inclination. Now, when the angle of inclination is given, what we're going to do is we're going to use the tan theta function to find its gradient. So it's pretty straightforward. It's just going into basically in reverse of what we were doing before. So let's have a look at an example. Find the points on the graph of f of x, where f of x is equal to x squared minus 6x plus 5, where the tangent has gradient -3 and the tangent has angle of inclination 45 degrees. Okay. So what we're going to do first is we're given gradient, so we need to work out, well, what's the derivative of this function going to be? So let's start off with our f of x. Okay. So f of x is equal to x squared minus 6x plus 5. So that means the derivative of this function is equal to 2x minus 6. Okay. So we're going to start off with this because we're talking about tangents. Okay. So as soon as we're talking about tangents, we're going to be doing something with derivative. Okay. So let's start with a. Now part A says the tangent has gradient -3. So that means that the derivative of this function is equal to -3. But if the function is equal to -3, what we can do is we can work out what our x value is. And once we work out our x value, we can then substitute it back into the equation to get what our y value is, and then that will give us the point. Okay. So here's our derivative. F dash of x is equal to -3. Okay. But our derivative is equal to 2x minus 6. So therefore, 2x minus 6 is equal to -3. So just solving this equation, we're going to get 2x is equal to, well, the -6 goes to the other side. We're going to get positive 3. So x is equal to 3 on 2. And so this is the x value of the point of our tangent, okay, or where the tangent has gradient -3. So what we're going to do is we're going to sub x is equal to 3 over 2 into f of x, okay? So f of x is x squared minus 6x plus 5, so f of x is equal to x squared minus 6x plus 5. So where x is equal to 3 on 2. So we're going to substitute that value in. We're going to get f of 3 on 2. So wherever I see an x, I'm going to replace it with 3 on 2. Minus 6 lots of 3 on 2 plus 5. Now I could do it the long way, or I could just put it into a calculator and get an answer, which I think is much easier. So what we're going to do is we're going to make sure we put brackets. 3 on 2, lots of x squared, or that is our x squared, I should say, minus 6 lots of 3 on 2, which is our 6x term. And then we're going to add 5, okay, and it gives us -7 on 4. And this is what y is equal to. Okay. So y is equal to -7 on 4. So therefore, what we can say is the tangent that has gradient -3 is at the point, this one's at the point, okay, and it's 3 over 2, comma, -7 on 4. Okay, so if we had the graph of x squared minus 6x plus 5, okay, and we looked at the point 3 over 2, comma, -7 over 4, and we drew the tangent along there, that tangent at that point would have exactly gradient -3. Okay, now let's have a look at number B. Now number B says the tangent has an angle of inclination of 45 degrees. So I'm going to do this one over here. Okay, so again, we need the derivative. So f dash of x is equal to, and this one's 2x minus 6 again. So same one. Now, the angle of inclination is at 65 degrees. We're looking for when it is at 45 degrees. So first, what we're going to do is we're going to write tan, okay, of 45 degrees. Okay, so we need to work out, well, what is the gradient of at 45 degrees? Well, what is the gradient when the line has an angle of inclination at 45 degrees? So what we're going to do is going to go tan 45, and if you know your exact values, you should know that that is equal to 1. So what we're doing is we're looking for when the gradient, so we are looking for when the gradient is equal to 1. Okay, because we're basically looking, so the gradient, or if there's an angle of inclination of 45 degrees, then that's going to correspond to a gradient of 1. So what we're going to do is we're going to work out, well, sorry, let me rewrite this. We're going to go, so we want when the gradient is equal to 1, that is, we want to know when f dash of x is equal to 1. Okay, but we already know that f dash of x is equal to 2x minus 6. So what we're going to do is we're going to substitute our f dash of x to get 2x minus 6 is equal to 1. Okay, I'm going to solve for x just like we did on the other side. So subtract 6 from both sides, we're going to get 2x is equal to 5, which means that x is equal to 5 on 2, or 2.5. Okay, so 5 on 2 is where the x value. Now we need to find the y value because we're finding the point on the graph where the tangent has inclination 45 degrees, which is, again, a gradient of 1. So to find y, what we're going to do is we're going to substitute our x value into our original equation again, or our original function. So our function f of x is equal to x squared. I think it was plus 5x from memory. Minus 6x plus 5. So it is important that we put it back into the original function because remember our gradient is a different function and it could correspond to a different y value. Okay, the x values are always good, but the y values is where we have the issues. So what we're going to do is we're going to substitute 5 over 2 into this. So we're going to get our 5 over 2 squared, where our x squared term is, and 6 lots of 5 over 2 for our 6x term, and plus the 5, okay? And so this is what our y value is equal to at the value, or at x is equal to 5 on 2. Okay, so we're going to put it into our trusty calculator. Okay, make sure we put brackets around this, otherwise it's not going to do it properly. So 5 over 2, all squared, minus 6 lots of 5 over 2, okay, plus 5. It equals, and we're going to get minus 15 over 4. So just to finish off, so the tangent has angle of inclination 45 degrees at the point, it's going to be 3, negative 2, just like that. Okay, so with that being said, that is our one for this slot. Okay, so what we're going to be doing next is we're going to be having a look at tangents and normals to a curve, okay, for the tangents and the normals. So I'll see you in the next one.